Most of us are familiar with the traditional role of the United States Army Corps of Engineers. They are designers, architects, and builders of logistical facilities. They establish forward airstrips, bunkers, and other fortifications. They clear enemy jungle hideouts, provide bridges and other stream crossing facilities. The engineers move with the American fighting man to help him go where he has to go, do what he has to do. Army engineers are also engaged in a number of research and engineering programs that are perhaps lesser known but equally important. On today's Big Picture, you will see some of the operations in two of these areas. The rivers and harbor studies, which provide valuable information for flood control and for best use of the nation's waterways. And the Army Nuclear Power Program, a significant development in the search for greater and more available power for military needs. Periodically around the world, there is tremendous damage and widespread loss of life when waterways overflow banks, dams, and levees. In many countries, social and economic disruption from this kind of natural disaster is usually devastating. In our own country, it is now possible to reduce some of the tragic losses caused by flood, thanks to constant research and development by U.S. Army engineers. This miniature river system at the Army Engineers Waterways Experiment Station near Jackson, Mississippi, is not a child's toy, although you might consider this man a modern Gulliver. He is one of the scientists at the station engaged in a research project which makes use of the largest miniature working model in existence. Covering 200 acres, the model, built to scale proportions, represents the Mississippi River and its tributaries. It is designed to aid in planning for the control and development of water resources in the mid-continent, which takes in almost a third of the nation. The need for a hydraulic engineering facility to analyze the movement of water and its effect on riverbanks and channels is evident, especially for the rich and fertile Mississippi River Basin. From the earliest westward drive of the pioneers, water and waterways have been the dominant concern of inland America. The Mississippi Basin contains many of the nation's greatest agricultural lands. Its rivers carry a flourishing commercial trade. Water is needed for industrial use, the movement of river traffic, and the generation of power. The rivers must be regulated and their waters utilized to provide for these needs. At times, however, water is a great liability. When floods descend upon the land, they reap a grim harvest of destruction and tragedy. To help prevent flooding of the land and to develop water resources for essential use is a tremendous undertaking. The Army Corps of Engineers has this responsibility. They've enlarged levees, built thousands of miles of new levees and hundreds of locks, dams, and reservoirs. Because of the size and number of these waterways controls, coordinating their operations is a complex and challenging problem. At headquarters of the Waterways Experiment Station in Vicksburg, Mississippi, scientists carry on research in various types of water studies. It was to help implement this research that the Mississippi River Basin model was designed. All important streams and adjacent lands which might be flooded are carefully reproduced in concrete at reduced dimensions. Miniature levees and embankments in the floodplain are built, some with removable sections to represent breaches or washouts. Forested areas are simulated by densely folded wire screens. The flow of water in the model corresponds exactly to the actual waterway it represents. 2.5 feet on the model is equivalent to 1 mile of actual distance. On the miniature, Sioux City and Council Bluffs are about 230 feet apart. The actual distance between the two cities is 90 miles. Time is also telescoped on the model. A 24-hour day is reproduced in slightly over 5 minutes. A flood which would travel from Sioux City to Omaha in 4 days will make the trip on the model in only about 20 minutes. To operate the facility manually would require a staff of over 200. Automatic controls have been installed to conserve manpower. The river networks on the model can be operated as a unit or in separate sections. The operation for a given set of conditions is controlled through a device by which holes in a moving strip of paper, much like the rolls of an old-time player piano, actuate valves feeding water into the miniature stream bed. A machine similar to a typewriter is used to punch holes in such patterns that the valves may be actuated in proper sequence. Precise records of the rise and fall of the rivers are obtained by electronically controlled probes which follow the fluctuations of the water. This data is transmitted for remote registration in the control houses. Time calendars keep continuous track of the date and hour at the model time scale. With these provisions, it is possible to reproduce any flood of the past or predict with accuracy what might happen under the worst possible future flood conditions. A dramatic example of the importance of the model waterway system took place during the 1952 flood on the Missouri River. With the terrible flood of the previous year still fresh in their memory, residents of the area learned they were to suffer an even greater disaster. 1,000 miles behind the scene, the model was quickly adapted to the actual flood situation. With amazing precision, the model predicted critical points on levees, areas in danger of flooding, and other vital information. This was the greatest flood yet recorded on the Missouri River in modern times. An area larger than the state of Texas was underwater. The Missouri River Division Corps of Engineers, drawing on its years of study and experience, had predicted the impending disaster. In cooperation with civil organizations, the engineers mobilized equipment, labor, troops, and trained flood-fighting personnel. Levees were reinforced. Those areas which could not be protected were evacuated. Meanwhile, the Waterway's experiment station had been alerted to prepare the Missouri River section of the model for round-the-clock operation. This would assist in predicting crest levels. Tests were begun 3 days before the flood crested at Sioux City and 7 days before it was expected to reach Omaha. Vital data was immediately furnished to the flood area. The first test quickly delineated the flood limits below Sioux City and revealed that some towns would be flooded, but certain other towns would escape flooding. The floodplain of North Omaha and the Council Bluffs region is several miles wide, but between the two cities it narrows to a few hundred yards. Floodwaters must crowd through this narrow passage. Tests indicated that the water would rise far above the levees and upper reaches of the narrow section. This forewarning gave flood fighters the information they needed to plan their battle. 5 days before the expected crest at Omaha, as predicted by the model, flood fighters worked at fever pitch, raising and reinforcing the levees which the model had shown to be vulnerable. Omaha and Council Bluffs were saved, and potential damages estimated at more than $60 million were averted. Today, our waterways are being managed by man for his own purposes by varied systems of engineering works. Flood stage forecasting is done quickly and more efficiently by computers. Though our mighty rivers are still subject to the whims of nature, their devastating effects can be controlled by man's ingenuity. The Mississippi River Basin model is a key installation in these control systems. As a mechanism into which waterways problems can be fed and answers produced, this facility of the U.S. Army Corps of Engineers works for the welfare of the American people. Solar power gave birth to our Earth. Across millions of miles of space, it radiated the heat and light that nourished the Earth's surface and made it flourish. But just as he has long been aware of the truth that solar power gives him life, man has also seen that on the Earth, progress is energized by power, and his constant search for new sources of power and heat has led him to the atom, to nuclear power. From a mass of uranium no bigger than a golf ball, he can provide light and heat for a modern shopping center for 1 month. From a power package this small, he can derive an energy potential equivalent to 6,000 barrels of diesel oil. This is of great interest to the Army, which uses enormous amounts of conventional bulk fuel for its many power needs. In the early 1950s, Army planners began studying the feasibility of a portable nuclear fuel power plant for battlefield support and for power needs at remote installations. The U.S. Army Engineer Reactors Group was assigned the task of working with the Atomic Energy Commission to develop a mobile reactor power package that could be moved anywhere. The concept of the portable reactor was first tested by Army engineers in 1960 in a very dramatic and very frigid setting. A great ice cap in Greenland was to be the location of the U.S. Army Polar Research and Development Center. Less than 900 miles from the North Pole, Army engineers began planning a city under ice, a camp to be built entirely below the ice cap surface. Providing power by conventional fuels would be impractical, especially during the winter months when transportation of bulk fuels would be hazardous. It was decided that a portable nuclear power plant would serve the camp's requirements efficiently. Construction of the camp moved forward as swiftly as weather and the flow of supplies permitted. Using heavy snow equipment to dig excavations, Camp Century, as a city under ice was named, began to take shape. Working conditions were far from ideal. Temperatures often went to 20 degrees below zero, and this was summer. When a trench was several feet deep, planks were put down on the shoulders of the cut. The planks would be used to support the roof of the camp. Soon the first roofing materials were put into place. Constructed of a series of steel arches, these roofs could be put up very quickly. Inside the completed tunnels, prefabricated and highly insulated wall sections were installed to make up living and working quarters for the personnel assigned to Camp Century. Specially reinforced Arctic structures were prepared to house the nuclear power plant. In a tunnel close to the surface, Army engineers built a maintenance facility to serve as both repair shop and garage. Components for the world's first portable nuclear reactor, designated PM2A, arrived at Thule, Greenland in July of 1960. This unit, part of a vapor container, weighed more than 21 tons. A wheeled caravan bearing the reactor components began the long haul from Thule toward the campsite. When the snow line was reached, the load was shifted to sleds for the final lap of the journey. The caravan moved to the ice cap over a route carefully planned by Army engineers to ensure the safety of the valuable cargo. Some components of the portable reactor were shipped in pieces and reassembled before being moved into the underground ice tunnels. The condenser, 15 tons of steel, was one of the first units to be moved into the tunnels. On small track rollers, it was slowly winched forward. Assembly of the nuclear plant was completed in 78 days by the crew which would operate it. For the first time in history, a complete portable nuclear power plant was being readied to serve the needs of the equivalent of a small city, without the use of a single ton of coal or barrel of fuel oil. As winter approached, the nuclear plant was ready to begin operations. Thanks to the reactor, all modern facilities were immediately available in the city under ice. Except for the fact that they had no windows, the men of Camp Century enjoyed spacious, comfortable quarters. The reactor under ice had ushered in an era of non-weapons use of nuclear power. Now Army engineers began to develop other applications for the portable nuclear reactor. In 1961, the Corps of Engineers, again in cooperation with the Atomic Energy Commission, planned the construction of a floating nuclear power plant. This would provide a mobile power source, essentially for Army operations, from offshore anchorage anywhere in the world. The reactor ship could also be used for civilian needs as an emergency power source in disaster situations. At Fort Belvoir, the Engineer Nuclear Reactors Group headquarters, contracts for the Army's first Waterborne nuclear power plant were drawn up. Construction and design features of the hull that was to house the reactor were carefully developed by Army engineers and the civilian contractor. From the mothball fleet of World War II Liberty ships, a vessel was selected for modification into a floating barge. Propulsion equipment was removed and the vessel was towed to a shipyard for the conversion operation. A new midsection was built inside the original hull to provide adequate protection for the reactor in case of collision or grounding. A crash into the barge's midsection by another vessel traveling at 20 knots would still leave a 1-foot barrier protecting the reactor area. About 900 tons of concrete poured between the double steel walls provide a shield up to 4 feet thick. This acts as both a collision barrier and protection for the operating crew when the nuclear reactor is functioning. Tons of polyethylene provide additional protection against radiation. The new double-bodied midsection was launched in April 1964. At a dry dock in Mobile, Alabama, operations began to splice the bow and stern retained from the original hull of the Liberty ship. The new floating barge was named the Sturgis in honor of the late General Samuel D. Sturgis, Jr., Chief of Engineers during the formative years of the Army nuclear power program. Next, the nuclear reactor container had to be moved to the dry dock for installation on the Sturgis. Along the route, power lines had to be temporarily taken down to allow for movement of the huge container. Army engineers planned special support for the roads that would have to bear its tremendous weight. At dockside, preparations had been made to receive the container, which was one of the largest single components ever to be transported over land. Special heavy-duty cranes and rigging equipment were used to position the container in the hold of the Sturgis. Each step in the construction of the barge and its reactor was preceded by model studies, allowing planning personnel to anticipate problems and make modifications if necessary. The reactor assembly was installed in the double-bodied midsection. Tightly sealed in a hull within a hull, the Army's first floating nuclear power plant would soon be ready for testing. Into the reactor core were lowered the fuel elements containing uranium. The elements in the Sturgis reactor can produce enough heat to generate 10,000 kilowatts of electricity, enough to provide power needs for a community of 20,000 people for more than a year without refueling. Operation of a power plant by diesel fuel for the same period would require 100,000 barrels. A steam conversion system was installed on the barge. This would utilize the heat derived from the nuclear fuel to produce steam for driving the generator. Operation of the Sturgis power plant was centered in a control room containing instrumentation for the entire complex nuclear and steam systems. Backup controls against failure of any component ensured safe and continuous operations. As the interior construction neared completion, finishing touches were applied to the outside of the Sturgis. Though the Sturgis would have no propulsion equipment of its own and would have to be towed, it was in every other respect a fully outfitted vessel with all the necessary apparatus for its job. The operating crew will not live aboard the vessel, but the midship deck house contains quarters for a 15-man tow crew, a galley, and a recreation room. At last, the 442-foot, 10,000-ton vessel was ready for trial. From its dock in Mobile, it began a 22-day journey around the tip of Key West, up the east coast to Chesapeake Bay, and into the Potomac River, where it would be docked at Fort Belvoir for several months of controlled testing. Monitored by the Army Nuclear Power Field Office at Belvoir, the tests were begun in the spring of 1966. Equipment performances were matched against the rigid specifications established for the floating nuclear power barge. All systems checked out okay for go. Certified as operational by all military and civilian agencies involved in its development, the MH-1A, Nuclear Power Barge Sturgis, was towed to sea in the summer of 1968 for its first practical application. Destination, Panama Canal. Assignment, to provide supplementary power for operation of the locks and other electrical needs. Increased commercial traffic due to the closing of the Suez Canal and additional traffic caused by the war in Vietnam, had taxed the Panama Canal's main water supply in Gatun Lake. 100 million gallons of water on each end of the canal must be moved in and out of the locks in order to raise and lower the ships. Diverted for this use, less water is available to generate power. At anchor and tied into the electrical complex at Gatun Lake near the first of the canal locks, the Sturgis's transmission lines carry electrical power generated by the vessel's nuclear plant to the shore facilities. As part of the power source, the floating nuclear plant is a valuable facility for the strategic canal zone. The men who operate the Sturgis reactor are graduates of a year-long nuclear power plant operators course, which is given at Fort Belvoir. Once assigned aboard the nuclear plant vessel, each man undergoes final training in his specific position. This ensures the high degree of responsibility essential for safe operation of a nuclear power plant. The Sturgis, a dramatic development in the Army's nuclear power program and the world's first floating nuclear power station. Nuclear reactors operated by personnel trained at Fort Belvoir's Reactor Center have been used to provide light and heat in various military installations, such as the McMurdo Scientific Research Station in Antarctica, where the remote location makes it impossible to bring in large amounts of bulk fuels in winter months. What projects lie ahead for the engineers? This artist's projection of a lunar module for NASA with its own nuclear reactor to provide power for space exploration symbolizes the advanced thinking of today's U.S. Army engineers. Whatever tomorrow's demands for research, development, or construction capabilities, the United States Army Corps of Engineers stands ready to serve the nation.